Our understanding of the universe's origin story hinges on a profound concept, the Big Bang. This theory is not just a cornerstone of modern cosmology, but also a fascinating narrative that has captivated scientists and thinkers for decades. This theory suggests that the universe as we know it began from an extremely hot and dense state approximately 13.8 billion years ago. At that moment, all the matter, energy, space, and even time itself were compressed into an incredibly small volume, a singularity. Imagine a point smaller than an atom containing all the matter and energy that would eventually become everything we see around us. This singularity was a place where the known laws of physics break down, and our understanding of space and time ceases to be intuitive. The Big Bang was not an explosion in the traditional sense like a firework going off in space. Instead, it was a rapid expansion of space itself, a stretching of the very fabric of the cosmos. This expansion was incredibly swift, occurring in a fraction of a second, and it set the stage for the universe's evolution. Instead, it was the rapid expansion of space itself, carrying all the matter and energy within it. This phenomenon, known as cosmic inflation, caused the universe to grow exponentially in an unimaginably short period, smoothing out any irregularities and setting the stage for the formation of galaxies and stars. This expansion continues even today, like the inflating surface of a balloon pushing galaxies farther apart. As space expands, it carries galaxies along with it, causing them to move away from each other. This ongoing expansion is a key piece of evidence supporting the Big Bang theory. The initial moments after the Big Bang were incredibly chaotic and violent. The universe was a hot, dense soup of particles where temperatures soared to unimaginable levels and energy was in a constant state of flux. The universe was unimaginably hot and dense, a seething cauldron of energy where the laws of physics as we know them were just beginning to take hold. During this time, fundamental forces such as gravity, electromagnetism, and the strong and weak nuclear forces began to emerge and shape the universe's evolution. In this extreme environment, the seeds of everything we observe today, stars, planets, galaxies, and even ourselves, were sown. As the universe expanded and cooled, particles began to combine, forming the first atoms. These atoms eventually clumped together under the force of gravity, leading to the formation of stars and galaxies. As we delve deeper into the Big Bang theory, we embark on a journey to understand our cosmic origins, tracing our lineage back to the very first moments of creation. This journey is not just about understanding the past, it also helps us comprehend the present and predict the future of our universe. It is a story of incredible transformations, from the birth of fundamental particles to the emergence of stars and galaxies, ultimately leading to the universe we observe today. Each stage of this transformation is a testament to the dynamic and ever-changing nature of the cosmos, a universe that continues to evolve and surprise us with its complexity and beauty. In the blink of an eye after the Big Bang, the universe embarked on a period of rapid expansion known as inflation. This was a momentous event that set the stage for everything that would follow. The universe, which was initially an incredibly hot and dense point, began to expand at an astonishing rate. During this epoch, space itself expanded faster than the speed of light, stretching the fabric of the cosmos like a rapidly inflating balloon. This analogy helps us visualize the sheer scale and speed of this expansion. Imagine blowing up a balloon. As you blow, the surface area increases rapidly, much like how space expanded during inflation. Imagine a tiny dot expanding to billions of light years across in a fraction of a second. This rapid expansion was not just a simple increase in size, but a fundamental change in the very nature of space and time. The distances between points in space grew exponentially, and this had profound implications for the universe's future development. This rapid expansion had profound consequences. It set the initial conditions for the universe's evolution, determining how matter and energy would be distributed. Without this period of inflation, the universe might have evolved very differently, possibly preventing the formation of galaxies, stars, and planets. It smoothed out the early universe, distributing matter and energy more evenly. This even distribution is crucial because it led to the uniformity we observe in the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation provides a snapshot of the universe when it was just 380,000 years old, showing us a remarkably uniform cosmos with tiny fluctuations. It also stretched out any initial fluctuations, creating subtle differences in density that would later give rise to the large-scale structures we observe in the universe today, such as galaxies and galaxy clusters. These tiny variations in density were the seeds from which all cosmic structures grew, driven by the force of gravity. As the universe expanded, it also cooled. This cooling was a critical process that allowed the universe to transition from a hot, dense state to a cooler, more stable one. The temperature drop was essential for the formation of atoms, which would later combine to form stars and galaxies. This cooling was crucial for the formation of matter as we know it. In the early universe, temperatures were so high that particles could not combine to form stable atoms. As the universe cooled, protons and neutrons could come together to form the nuclei of atoms, and eventually electrons joined to create neutral atoms. In the extreme heat of the very early universe, energy was constantly converting into matter and antimatter and vice versa, in a cosmic dance of creation and annihilation. This process was governed by the laws of quantum mechanics, which dictate that particles can spontaneously appear and disappear. However, as temperatures dropped, this symmetry broke down, allowing a slight excess of matter to persist. This asymmetry is one of the great mysteries of cosmology, as it explains why there is more matter than antimatter in the universe. Without this imbalance, the universe would be a very different place, possibly devoid of the matter that makes up stars, planets, and life itself. This surplus of matter would eventually form everything we see in the universe today, from the smallest particles to the largest cosmic structures. Over billions of years, gravity pulled this matter together to form stars, galaxies, and clusters of galaxies, creating the vast and complex universe we observe today. The story of the universe's rapid expansion is a tale of transformation, from a hot, dense point to the magnificent cosmos we inhabit. In the first fractions of a second after the Big Bang, the universe was a seething cauldron of energy, with temperatures reaching trillions of degrees. This was a time of unimaginable heat and density, where the very fabric of space and time was in a state of flux. The energy levels were so high that the fundamental forces we know today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. Under these extreme conditions, energy began to condense into matter, giving birth to the fundamental building blocks of our universe. This process, known as baryogenesis, saw the transformation of pure energy into particles. It was a delicate balance, as matter and antimatter were created in almost equal amounts, but a slight asymmetry favored matter, allowing it to dominate. Imagine a cosmic soup of particles colliding at unimaginable speeds. This was a chaotic and violent environment, where particles were constantly being created and annihilated. The universe was a hotbed of activity, with particles smashing into each other, creating new particles in the process. Quarks, the fundamental particles that make up protons and neutrons, came into existence. These tiny particles are the building blocks of the atomic nucleus. Quarks come in 6 different types, or flavors: up, down, charm, strange, top, and bottom. In the early universe, up and down quarks were the most prevalent. Along with them, leptons, the family of particles that include electrons and neutrinos, emerge from the primordial energy. Electrons are essential for forming atoms, while neutrinos are elusive particles that rarely interact with matter. These particles played crucial roles in the evolution of the universe. These particles were constantly interacting with each other, governed by the fundamental forces of nature. The interactions between quarks and leptons were mediated by force-carrying particles known as bosons. The strong force, carried by gluons, was responsible for binding quarks together, while the weak force, mediated by W and Z bosons, played a role in particle decay processes. The strong force, responsible for binding quarks together, was particularly dominant in this early universe. It was the glue that held quarks together to form protons and neutrons. Without the strong force, the atomic nucleus could not exist, and the universe as we know it would be vastly different. It was so powerful that it momentarily overwhelmed the other forces, creating a unique state of matter known as quark-gluon plasma. In this state, quarks and gluons were not confined within protons and neutrons, but existed freely in a hot, dense soup. This quark-gluon plasma was a fleeting phase, lasting only microseconds, but it was a critical step in the evolution of the universe. As the universe continued to expand and cool, the strong force began to weaken, allowing quarks to combine and form protons and neutrons. This cooling process was essential for the formation of stable matter. As temperatures dropped, quarks found it increasingly difficult to remain free and began to bind together, forming the first protons and neutrons. These particles would later become the building blocks of atoms, the basic units of matter that make up everything we see around us. The formation of atomic nuclei marked the beginning of a new era in the universe's history. Protons and neutrons combined to form the nuclei of the first atoms, primarily hydrogen and helium. These simple atoms would eventually give rise to the complex structures we see in the universe today, from stars and galaxies to planets and life itself. As the universe expanded and cooled, a pivotal transition occurred, the formation of atoms, which changed everything. This marked a profound shift in the nature of the universe, from a hot, opaque plasma to a cooler, more transparent state, fundamentally altering its structure. Initially, the universe was filled with a sea of free electrons and protons, forming a plasma that scattered light like fog, making it impossible to see through. As temperatures dropped, the electromagnetic force, which governs the interaction between charged particles, became strong enough to bind electrons to atomic nuclei, forming the first atoms. This process, known as recombination, began about 380,000 years after the Big Bang, marking a significant milestone. It marked a turning point in the early universe, as the formation of neutral atoms allowed light to travel freely for the first time, illuminating the cosmos. The universe, once a glowing fog, became transparent, allowing us to peer back in time and observe this era through the cosmic microwave background radiation. The formation of atoms was a crucial step in the evolution of the universe, setting the stage for future developments. It paved the way for the formation of stars and galaxies, and ultimately for the emergence of life itself, a remarkable journey.